Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and very good day I bid to all those watching. So before we start, I'm going to introduce myself. My name is Nur Amelia Diana binti Azman. I'll be the first one to teach the first subtopic for our unit for today, which is limits at infinity and behavior of a function. So let's move on to the first subtopic for today, which is limits at infinity and horizontal asymptote. So please remember that when the question is asking for limits at infinity, infinity can go either two ways, positive or negative. Since it's a limit question, so the question will always go limit f(x) as x approaches something, right? And limit at infinity, it's either positive or negative infinity. There will never be a question where there is neither positive or negative, unless of course it goes like this, then it has both. But anyway, that is not what we're going to talk about today. We're talking about how we are going to read out from a graph and then project it into the answer. So let's take limit x approaches to positive infinity for a function f(x), and then a limit for x approaches a negative infinity for a function f(x). For example, let's take a simple one. The function f(x) equals to 1 over x. 1 over x is this. This is the function. This is the x, and this is the y. So to read it, you have to read the value on the first value, move from x on the x-axis, and then move it to the right when it asks for positive. Positive here, right now, positive, it moves to the right. Notice how the graph moves from 0 to positive infinity this way towards 0. What about negative? Then the opposite way. It also approaches 0. It never really touches a direct point, a single point, but it moves approaching that point. As x moves approaching positive infinity, where does it approach? It is approaching 0. And the same happens. So the value would become 0 despite the fact that it never touched the 0 value of y in the first place. And so we can see here that there is a horizontal asymptote formed. A horizontal asymptote is a horizontal line, right? Is a horizontal line, usually dotted, or even in the x-axis itself. And the graph would never touch it. So for this one, the horizontal asymptote would be 0. But what about for a different graph? For example, if it goes like this, it never touched the value 1. It never goes below 1, but it goes over 1. So you can say that the horizontal asymptote is equals to 0. So you can write as in x asymptote is equal to 0.
So this is an example of limit at infinity and horizontal asymptote. So we look at the question A. This is limit of function 1 over x when x is approaching to negative infinity. It says that is equal to 0, so let's see what happens. So we can observe from this graph. Okay, let's say we take any point on x-axis. So we take this point. So when at this point is moving to the left-hand side, we can observe from this graph, the point of y-axis is nearing to 0. So we can say that when limit of function 1 over x is equal to 0, when x is approaching to negative infinity. So we look at the second question B. This limit of function 1 over x when x is approaching to positive infinity is also equal to 0. So we can also observe from this graph. So we take any point on x-axis. Let's say we take this point. When x is moving to the right-hand side, the point on the y-axis is nearing to 0. So we can say that limit of function 1 over x when x is approaching to positive infinity is equal to 0 also. And how about the horizontal asymptote? We can see that the graph didn't touch any point on the x-axis. So we can say that the horizontal asymptote for both graph is x-axis.
Hi guys, welcome again. So now it's time for the second subtopic for the unit, which is limit laws that are exclusive for limits at infinity. And don't worry, this topic is really easy because there's only 3 items you gotta remember, which I have already shorted it. So for your own convenience, which is our acronym for today, PSS. I think you can see it. PSS. well, it's not pusat sumber sekolah either. It's actually for power, scalar, and scalar as well. Well, single scalar. Okay, so power. For if the limit is x approaching positive infinity and the function has a power outside of it, then you can take the power, out. So it would be limit f(x) as x approaches positive infinity and the power is outside. So that means you won't have to take into account of making a positive infinity to the power of something. So it's much easier. And same thing happens when it's a limit x approaching negative infinity. X approaching negative infinity f(x), but this one also has a power n, so you can still bring n to the outside. Bring n outside, so x approaching negative infinity f(x), where the n is outside. So that's for power. Well, now what about scalar? For example, for if the limit x approaching positive infinity has a scalar that you can get out or like extract from the function, then you can take it out. The same thing happens. So it would be equals to k limit as x approaching positive infinity of x. And the same would apply for negative infinity, just as listed. Now what about single scalar? Now this is somewhat like this, but just minus the function. So it's single. They don't have any more partner of the function. So it's just for a limit as x approaching positive infinity k. See how for k there is no n, so it's just equal to k, nothing more. And the same would happen for x approaches negative infinity k, then the answer would still be k. So now I'm going to teach you two more subtopics, and don't worry, it's going to be really easy. Just as easy as before. So the first topic will be infinite limits at infinity, and the second one would be limits of x to the power of n as x approaches positive or negative infinity. Now for the first one, before we get into it, I think it's best if we have a quick clarification of the difference between infinite limits and limits of infinity, so that you can truly understand what everything is. So infinite limits is when a limit x approaching to anything. It could be it could be it could be a, it could be b, it could be positive, it could be anything, any number of a function, and the answer would be positive or negative infinity. That is an infinite limit, where the limit answer is positive or negative infinity. While a limit at infinity is when a limit x approaches something for a function, and is when x approaches positive or negative infinity, and then the limit is something. It could be a, it could be b, it could be l. So when infinite limits at infinity, it is a combination of both. So it would be when the limit x approaches positive or negative infinity for a function of x is positive or negative infinity. There's going to be one in the front and one in the back, just like the topic. And now this type of phenomenon will usually happen for functions of x to the power of n. And don't worry, no matter how high the n is going to be, the answer will always be the same. For a limit as x approaches positive infinity, any number, any positive number, it's gonna be positive infinity. But it's a different case for the limit x approaching negative infinity. Okay, because it differs. If it's an odd number, it's gonna be a negative infinity. But if it's an even number, it's gonna be a positive infinity. Take note that this is only for with the power which is higher than zero. The power that is positive powers only. So so to make it clear, I think we should see the graphs. So let's take for example x to the power of n. The graph would be a simple straight line. See, x to the power of 1. This is a y equals to x graph. As x approaches positive infinity, it is positive infinity. As the x increases, y increases. What about y equals to x squared? For this one, it's going to be a smile. A wide smile. As x approaches positive infinity, it is positive infinity. X increase, y increase. And then for x approaching negative infinity, it is rising, it is increasing in the y value. So x approaches negative infinity, positive infinity. And then what about for x to the power of 3, the cubic, a perfect cubic one? It would be like this. Minus something like this. X approaches positive infinity, it still approaches positive infinity. X approaches negative infinity, it is negative infinity. Now, what about a much scarier one for most, which is x to the power of 4? I hope you can see this. Then it's just going to be, surprisingly, a smile. But it is much narrower compared to x squared. As the x increases, the smile for only odd graphs is going to be a narrower smile. And so still, it's going to be the same. As x approaches positive infinity, y is increasing. So it's a positive infinity. As x approaches negative infinity, it is still increasing. This is for an even number, and this is an even graph. Well, x to the power of 5, for clarification's sake, it's just going to be an even narrower version of x cubed. This is an x to the power of 5. So when x approaches positive infinity, it increases, it's a positive infinity. X moves to negative infinity, it goes negative infinity. Follow the graph. See? It's very simple.
So this is an example of limit of x power of n as x approaching to positive infinity. So we look at question 8. Limit of 2x power of 5 when x is approaching to positive infinity. So we need to sub in the positive infinity to the x and will become positive infinity. Look at the question B. The limit of negative 7x power of 6 when x is approaching to positive infinity. So we need to sub in the positive infinity into the x also. But since we have the negative in this function, so we need to give back write back negative.
Okay, let's continue with limits of polynomial as x approach to negative infinity. My friend just now has explained when x approach to positive infinity. I have here to explain to you guys when x approach to positive infinity. Here are some things. When x power of n, when limit x approach to negative infinity, the answer will be positive infinity if the n here, power or the n here is even number. And the answer will be negative infinity if the n or the power is the odd number. Okay, we'll look at the example. A. Negative 4x power of 8 plus 17x power of 3 minus 5x plus 1 when limit x approach to negative infinity. Okay, first thing first, we must take the highest degree term. Okay, when we see here, what is the highest degree terms? Here, the highest degree terms is negative 4x power of 8. So, we write back the equation like this. Negative 4x power of 8. Okay. As we can see here, the power or the n here is the even number. Here is the even number. So the answer will be positive infinity. But we must carefully here, we have sign here. We have sign here which is negative. When negative positive, the answer would be negative positive, the answer will be negative infinity. Okay.
This is just one concept you have to remember when the question limit x approaches positive or negative infinity, and the function is a function where you have a polynomial of much higher numbers than usual. For example, let's do a more abbreviated version. C0. This is a C0 with no x, and then you have a C1 with an x to the power 1, and then you have a C2 to the power of x squared, and then you have a C3 to the power of x cubed, and then blah 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 until you have plus a Cn to the power of x to the power of n. Now it's gonna be a really long function and so tiring. So the easiest way out is to just find the limit of x approaches positive or negative infinity for the highest number, the highest degree of power for x, not for any other number, but just for x or whatever unknown is here. So x approaches positive infinity. So just take in for Cn to the power of xn. That's just as simple as that. No need to take into account any of these other pesky numbers. Just take the largest one, because the limit is still going to be the same. It follows the highest degree of power in the function. That's it. That's all for me. Now, that's all for me.
This is an example of limit of polynomials when SS is approaching to positive infinity or negative infinity. So we look at question 8. Limit of function x plus 4x plus 5x power of 2 plus 6x power of 3 minus 7x power of 5 when x is approaching to a positive infinity. So we only take the highest degree terms, which means it's negative 7x power of 5. So we write again this formula. So we start in a positive infinity inside x. So we will give an answer positive infinity. But since it's a negative function, so we need to write back negative. So the answer is negative infinity. We look at the question B. Limit of function x plus 4x plus 5x power of 2 plus 6x power of 3 and plus 7x power of 4. We are also taken the highest degree term. So we take 7x power of 4. We write again this equation. When x is approaching to negative infinity, we start in the negative infinity inside. But since the power is even number, so the final answer will be positive infinity. Here we have one subtopic, identity as infinity, which is limits of rational function as x approaching to positive or negative infinity. And here we have a form of rational function to determine the behavior of a rational function. The technique we can do is by dividing each term in numerator, here is numerator, and denominator, here is denominator, by the highest power of x.
Let's move to the limit of rational function as x approach to positive, negative, infinity. Okay, first thing first, we must try to substitute positive infinity at the equation. So when we try to substitute, we will get this form, which is we call indeterminate form. So when we get like this, we must try to get the solution. Use three ways here. We just factorize, multiply with the conjugate, divide by the highest power of x. Okay, here the best ways to use is divide by the highest power of x. So we here the highest power of x is power of 1. So we must divide the numerator and denominator with x power of 1. So here you can see 3x over x plus 5 over x divided by 6x over x minus 10x over x. So can we simplify here? Simplify, we will get like this. So when we get like this, so we can substitute the positive infinity here. When 5 over infinity, the answer will be 0. So when we get more simplified, we get the answer will be 1 over 2. We also have another ways to use when we get like this question. We also can divide. We can also divide by the highest numerator and also the denominator. We can see here the highest of denominator numerator here is x power of 1, and the denominator is also x power of 1. So we just can write we just take this and write back like this. We just write back limit approach to positive infinity 3x over 6x. When we simplify, we also get back the answer also same, which is 1 over 2.
As we know how to solve the limits of rational function, we also have a quick method for this situation as x approaches to positive infinity or x approaches to negative infinity. Here, as you can see, the end behavior of this polynomial matches the end behavior of its highest degree. So the numerator can be divided by the highest power of denominator. Next, this function is also, we have the highest power degree of numerator and denominator is y. So after we substitute the positive infinity into this function, we can conclude that the answer is a real number, which is 1 over 2. This is an example of quick method for finding limit of rational function as s is approaching to a positive infinity or negative infinity. So we look at question A. Limit of function 3x plus 5 divided by 6x minus 5 when x is approaching to a positive infinity. The quick method is we are using the highest degree terms of the numerator divided by the highest degree term of the denominators. So we can see that this is the highest degree term. So we write again the equation 3x divided by 6x. Since it can be simplified, so we cut the x and we can get the answer 1 over 2. Look at question B. Limit of function 4x power of 2 minus 2x minus 1 divided by 1 minus 3x when x is approaching to a negative infinity. So we also take the highest degree term, which is 4x power of 2 divided by negative 3x. We simplify it and we can get negative 4 over 3x. We submit the negative x, negative become positive, so our final answer is positive infinity.
Okay, we continue with limits involving radical. Here we have three choices. First choice is when square root x power of 2 equals to modulus x equals to x. Second choice is when square root of x power of 4 equals to modulus x equals to x power of 2. The third choice is when square root x power of 6 equals to modulus x equals to x power of 3. When we get this pattern of question, we will not disturb this part. When the question limit at approach to negative infinity, this part will be always positive, will not be negative. This will not change. Yeah, we will disturb is the bad part here. For example, like this, when limit at approach to positive infinity, will be x power of 2, x power of 3. But when limit at approach to negative infinity, the bad part there will be negative x power of 2 and negative x power of 3. So let's move to the example. As we can see here, when square root x power of 2 plus 2 divided by 3x minus 6, when limit at approach to positive infinity. So when we look at this equation, the best choice is the first choice. So we will divide the numerator with square root of x power of 2 and the denominator with x. Okay, why we not divide this numerator with power of x power of square root x power of 2? Because here we can see they don't have square root. So, but we still can use divide by x because this is still the same pattern. So when we simplify and here we substitute the positive infinity when 2 over infinity we get 0. So when we simplify, we will get the answer will be 1 over 3. Okay, let's when we find the question negative infinity here, okay, negative infinity here, okay, we will divide, this will change. Like I just explained just now, when we make the equation limit at approach to negative infinity, this will change, which will use negative x. So here will be negative x. Here will be negative x. So here will be negative x. So here will be negative x. So when we multiply, we will get this like this. So here when we substitute negative plus negative, here the answer will be negative. Will be negative 1 over 3.
Lastly, I would like to explain about the end behavior of trigonometric, exponential, and logarithmic function. Here we have the graph of y equals to sin x, which is a trigonometric function. Why this function does not have limit as x approaching to positive or negative infinity, which is fail to exist, because the value is vary between -5, here -5, and y without approaching any specific spaces. Okay, for the exponential function, here we have the graph of y equal to ln x and y equal to exponent x. For the limit notation, for limit approaches to positive infinity, ln x, for this graph ln x, when x is approaching to positive infinity right here to the right, the graph will be go to the upside and the answer will be positive infinity. Next, for the limit x approaching to positive infinity, for the graph exponent power of x, it will give the same answer because both graph will increase. So the answer also positive infinity because both increase. You can see here increase without bound as positive infinity. Okay, next I will explain about this graph. It's about y equal to exponent power of x. Here we want to learn about the reflection of this graph. As we can see, the graph is like this: y equals to exponent negative x, because this graph is the reflection of y-axis of the y equal to exponent power of x. So the limit notation we have in this situation, when x approaching to positive infinity, exponent negative x, the answer will be 0 because it is approaching to 0 values.